Alright, now we want to look at adjusted R squared. So I have the same 5 predictor variable data that I had in the previous video. I did change the responses a bit, so these are slightly different numbers. And I went ahead and reran the multiple linear regression. Again, notice the order of the predictors is reversed in the output. And I looked at the ratios again of the slopes to the standard error. And now this time I got something a little different. I actually got a 2.47 here, which would say, yeah, maybe this is significant here. P-value of, I'm not sure exactly what it would be, but it would be maybe 0.02 or 0.03, somewhere in there. And the other numbers are very large. And so now we want to look at adjusted R squared. So up here is our R squared. To get adjusted R squared, we use this formula here. So the one right above where I've highlighted, it's 1 minus R squared times n minus 1, where n is our number of rows, divided by n minus k minus 1, where k is the number of predictor variables. Now, this bottom part, so here I mentioned that formula again, n minus 1 over n minus 1 minus k. That's the same as taking n minus 1 divided by the degrees of freedom right here, the 24. And so you could do this all in one formula, but it might be a little easier to do it in pieces. So here I'm going to take my n minus 1. So there I could do a count or something, but somehow I need to know the number of rows. It's 30 in this case, minus 1. Then divided by, and I can just go up here and click on my degrees of freedom. I could put in the 30 minus 5 minus 1. I would get 24. And hit enter. So I get that number. Then I'll do equals 1 minus my R squared. Do that. And then equals 1 minus this 1 minus R squared times this number here. And so I see my adjusted R squared is about 0.952, whereas the R squared was about 0.96. So looking at the variables, again, definitely predictor 5 did not look significant. So I wonder about throwing it out. And so I'm going to highlight this stuff and copy it. And then if I go to sheet 2, this is where I threw out predictor 5, so it's not in the mix here. I reran the multiple linear regression and got an R squared here of 0.957, a little below what this one was. This was 960. But the question is, well, how does that compare an adjusted R squared? And if I put it in the same spot, so here I was 2 lines below my ratios, and over to the left by 1. So I'm in that same spot. I'm going to paste. And so here I see that this number went down a little bit from 1.2 to 1.16. My R squared, 1 minus R squared is there. And I computed a new adjusted R squared just using the same formulas from here, just by doing copy and paste. And actually, I'm a little surprised. The adjusted R squared here is a little bit higher than here. not much higher, only what 0.002 higher, and so the adjusted R squared here is a little closer than the original R squareds were. This is off at 0.002. This was 0.96. This was 0.9. So I've cut it in about half, because this, maybe even a little less than that. So I'm actually kind of surprised. I would have thought the adjusted R squared here would have been higher than in the previous case. That's okay, you know. That's the thing in working with data. You can be surprised. And so, though I'd still say I think I would rather use this model with just the 4 predictors than the first model, because here these 3 look significant. Predictor 1, predictor 3, predictor 4. Now actually notice predictor 2 looks a little less significant. It's getting closer to 2.1. And so I could do the same thing again. I could highlight all this, copy it, go here where I took out predictor 2 and look at the result here. And what I see is that the adjusted R squared went down a little bit more, which again, to tell you the truth, I'm kind of surprised. But it's really a matter of looking at all of these items. So I want to look at these ratios for the significance of the slopes. And again, here, 2.177 with 30 rows, that would just barely be significant. You know, I think probably a p-value of around 0.04 or so. You could test it and see. But it wouldn't be really significant. It wouldn't be a really small p-value like these other 3 would. And I'm not really worried about the intercept. And I do see the adjusted R squared has gone down a little bit. And the whole point with the adjusted R squared is this number here, where we take n minus 1 divided by n minus 1 minus k, or n minus k minus 1. What happens is, as k gets smaller, this number also gets smaller, is what you notice. And so when I take the 1 minus r squared, which is my sum of squared errors, I'm multiplying it by something a little smaller, and by multiplying that by something a little smaller, when I subtract it from 1, it makes it a little bigger. So the whole idea is adjusted R squared wants to help out models that have many fewer variables in them, so 3 as opposed to 5, that sort of thing. It's trying to help that out, and in this case we see, well, it helped it out a little bit, but actually the adjusted R squared is still a bit smaller for this model. But again, I think I would probably pick this model with the 3 predictors over the model with the 5 predictors or 4 predictors, based on the fact that these other 2 slopes weren't that significant. Well, this one wasn't at all in predictor 5. This wasn't that significant. And my adjusted R squared did not suffer very much in going to fewer variables. You know, fewer variables is much simpler, and so I like that better. And that's what you're doing with adjusted R squared, is you're comparing more than just the slopes and the significance of the slopes. You're trying to look at the model on the whole, using the adjusted R squared. But again, the adjusted R squared is trying to help us by saying, that actually fewer variables does tend to be a nicer thing, and so it tends to penalize us if we try to have too many variables.